Okay, this is the second video for related rates, and we're going to look at a different type of problem than what we were doing before. We're flying a kite at the end of a 100-foot string. The goal is to find the change in height of the kite when its horizontal position is changing at a rate of -2 feet per second, and it's currently 60 feet off the ground. So let's see if you can take a moment and draw a picture of this and define all of the variables that you know. Pause the video and go do that. Okay, welcome back. Let's draw in what we know. And let's just say that this kite is attached to the ground. That way we don't have to worry about how tall the human being is that's holding it. Well, that was horrible. Thank you, Unity. Sorry, thank you, Notability. All right, here we go. 100-foot string, there's a kite that's flying in the air. Let's just call the string, let's call it C. I don't want to use S for string because it just looks like a 5. The string is 100 feet long. Okay, the question says, find the change in height. So the variable for that is change in height, change in time. dH dt is what we're looking for. So I'm going to call this the height then. So find the change in height of the kite when its horizontal position is changing at a rate of -2 feet per second. So that means that the kite's horizontal position is changing in that direction by -2 feet per second. Let's call this side of the diagram, let's call that x. So then we can say dx dt is -2. The negative means the horizontal position is moving in the left direction. Okay, so we've got the horizontal position is changing and it is currently 60 feet off the ground. So we know that h is equal to 60 feet. All right, there's our diagram. These are the variables that were given to us and that we're looking for. Now the next step is to try and relate all of these variables together. Well, I can see here that this is looking like a right triangle to me. And the three sides are related to each other using the Pythagorean Theorem. So I can say x squared plus h squared will equal c squared. All right, we've got our first 3 steps. We've drawn a diagram, we have the variables, we have an equation that relates all of our information. Now we're going to differentiate this with respect to time. Differentiating with respect to time means we are going to use the chain rule on each of these variables. So for x squared, the outer function is the squared. So I'm going to bring the 2 out in front without changing the x. And then I'm going to multiply by the derivative of x. So that's dx dt. For the height squared, that's 2h dH dt. And finally for C, the string, that's 2C dC dt. Okay, the last step is to plug things in. So let's start plugging things in. So I have 2, but it didn't give me x, so I'll just write x for now. dx dt it did give me, that's -2. H they told me was 60 feet. dH dt is what we're looking for. C they told me was the string, that is 100, and I don't know dC dt. So this is kind of a problem because we're missing too many different variables. We don't know x, we don't know dC dt, and we're looking for dH dt, so that should still be a variable in your equation. So let's see if we can find some of these. Well, the information they've given us so far, I'm going to write some of my work off to the side here. The information that they've given us so far is that at this very moment in time, we know that this side is 60 and that side is 100. So at this instance, we can use the Pythagorean theorem to find x. So we have 100 squared equals x squared plus 60 squared. And doing some math or recognizing this as a 3, 4, 5 right triangle, we know that at this moment, x is 80 feet. Okay, we can make that substitution then. Now I can say this is 2. Right now at this moment, x is 80, negative 2. 2 times 60. dH dt is what we're looking for, so that's a variable we're okay with. And the next thing, or the last thing we need to find, is what is dc dt? In other words, how is the string that's holding the kite changing? Well, this string is a constant. The string is 100 feet. The string will always be 100 feet until we start reeling the kite back in, but that's not what we're talking about right now. We're talking about this string being 100 feet and the kite flying in the air. So dc dt, even though it didn't tell us, dc dt in this case is 0 because the string is a constant length. And we found x is 80 feet at this moment in time. Okay, last but not least, let's do some math here. 2 times 80 is 160. 160 times negative 2 is negative 320. 2 times 60 is 120 dh dt. And 2 times 100 times 0 is just 0. If we isolate dh dt, I'm going to add 320 and divide by 120. Okay, those zeros will reduce, and if I divide everything by 4, I will get 8/3. Now let's talk about if that 8/3 makes sense. Does it make sense that dh dt is positive? Does it make sense that the height is increasing on this kite? Let's think about the fact that the string that the kite is attached to is never changing its length. So if the kite is indeed moving to the left, getting closer to being above you, and that string stays a constant 100 feet, that height should indeed be increasing. The kite should be going higher up in the air as it comes closer to you over your head. So a positive 8/3 makes sense. Now we have to think about what the units are for this. Since we're talking about height, the units in this case will also be in feet, and the time is in seconds. So that means at every second that goes by, the kite is getting 2 2/3 feet higher up in the air. Okay, that was good. That was the first question. Let's stick with the same kite in the same moment in time. And I'm going to ask you a different question this time. This time, the kite string makes an angle with the ground. At what rate is the angle changing at that same instance as the first question? Take a moment, pause this, see how far you get. Draw the diagram, define your variables, see if you can set up an equation and actually start differentiating. When you get to a point where you're absolutely stuck, come back. Okay, welcome back. It's the same instance. So we still have the kite in the air. We still know that I'll still call this C, I'll still call this H, and I'll still call this X. So at this moment in time, we know that H is 60, because that's what they told us before. We found dH dt in the last problem, and that's 8/3. They told us what C was 100, and after our discussion in the last problem, dc dt is still 0. The string is not changing its length. We did some math, and we found that x was equal to 80, and we know that dx dt, so that change, that horizontal value is changing by -2 feet every second. So the kite's coming closer to you. This says, though, that the kite makes an angle with the ground. So here, that's the angle that we're looking for. The question says, at what rate is the angle changing? So what we're looking for is d theta dt. That is an unknown. You can find the measure of the angle at this moment, but I'll tell you that we actually don't need to. Let's do some things with the variables we do have. Since we're working with theta, we're working with the angle, let's use some trigonometry. I'm going to use the opposite side and the adjacent side. So that means I'm going to use the tangent of theta. The opposite side is h, and the adjacent side is x. All right, so we've done our 3 steps. We have drawn the diagram, we've declared our variables, we have written an equation. Now, before we plug anything in, we're going to differentiate this. Okay, let's find the derivative. We're going to find the derivative of tangent theta. We need to use the chain rule. So the derivative of tangent, secant squared, without changing the inner function, multiplied by the derivative of the inner function, d theta dt. On the right-hand side, we get to use the quotient rule. So the quotient rule will find the derivative of the numerator times the denominator unchanged minus the numerator times the derivative of the denominator, all over the denominator squared. Okay, last step now is to plug things in. Secant squared theta is going to take us a little bit of work. So let's do a little bit down below on what secant squared theta is going to look like. So we have secant squared theta. Let's talk about what we know. Secant squared theta is the reciprocal of cosine. And cosine squared is the same thing as cosine of theta times the cosine of theta. Well, the nice part is, in the triangle that was given to us, we can actually find the cosine of theta. If that's theta, we know that this is 60, that's 80, that's 100. Cosine is adjacent over hypotenuse. So the cosine is 80 over 100 times 80 over 100. I'm going to reduce that because there's no way I would like to multiply that in my head. So 80 over 100 reduces to 4/5. 4/5 times 4/5 is 16 over 25. And 1 divided by 16 over 25, I'm going to flip and multiply, is 25 over 16. So we just did some work without a calculator to figure out what the secant squared of theta is equal to. And secant squared of theta is equal to 25 over 16. So let's go back up to our equation here, up to the problem, and we're going to replace secant squared with 25 over 16. We're looking for d theta dt, so we'll keep that in there. And now, because of the last problem, we know a lot. dh dt is 8/3. Ooh, I should move this down a little bit. I'm going to write this a lot bigger, actually. Okay, so let's write this a little bit bigger. We have 25/16 times d theta dt equals dh dt we found was 8/3 in the last problem. X we know is 80. H is 60. dx dt is -2. And x squared is 80 squared, or 6,400. Oh my goodness, this is going to get big. All right. I would say honestly at this point, well, nope, let's do it by hand. It's good for us. d theta dt, it's good for us. 8/3 times 80 over 1 is 640 over 3. 60 times -2 is -120, so this becomes plus 120 over 3. Sorry, over 1. What we need to do is get a common denominator on those two fractions on top. So if I multiply this fraction times 3 over 3, that gives me 360 over 3. And 360 plus 640 is 1,000, luckily. I'm going to move my extra work down a little lower. Okay, so this is 360 over 3. 360 over 3 plus 640 is 1,000. So now if I flip this and multiply, it becomes 1 over 6,400. 1,000 and 6,400 will reduce to 6.4. Is that right? For some reason, that doesn't feel right. 6,400 divided by 1,000. Yeah, 6.4. Oh, this is getting ugly. Okay, finally, to isolate d theta dt, I'm going to multiply by 16 over 25 on both sides. So this will be 16 over 25. And that's good. We're going to leave it like that. If you had a calculator, you would go further, but if you didn't, we're good. So well done. There it is. Oh wait, we need to have some units. So what are the units? This is an angle measure. How are angles measured in trigonometry? They are measured in radians per second. Okay, that's it.